Hello, this is the example class for linear algebra part of this course. And in this example class, we'll go over problems of 2013 exam, only linear algebra part, and we will slowly solve them. Okay, so let me start with the problem A1. Yes, this is a more or less true-false statement. Part A is false. It's enough to provide a counterexample. Okay, let me remind you that the assertion is this: u plus v is u squared plus v squared plus 2u dot v. Okay, good. So to find a counterexample, it's enough to find two vectors, for example, say that this is positive and this is 0. Yeah, for example, if we take u to be minus v, the left hand side is 0 and the right hand side is positive. Yeah, unless both u and v is 0. So the simplest counterexample is going to be n equal 1. Yeah, all these vectors lives in n-dimensional space. And u is vector 1, yeah, and v is vector minus 1. Okay. In the left hand side we get 0, and the right hand side we get 1 plus 1 plus 2 is 4, not 0. Contradiction. Okay. Yeah, if you don't like this counterexample, you can take n equal 2, and you can take u to be vector, say 1, 0, and v to be minus u, and you get, of course, the same counterexample here. You get the same thing. Okay, this is part A. A1. Part B is actually correct. This is true. And then we have to prove it. Let me remind you what it says. It says that if you have two vectors in R2, which are both non-zero, and such that they are orthogonal, then they span R2. Then span of u and v is R2. Yeah, this is true. Let me give a short proof. Okay, so first let's say the easiest, there's many ways how to prove it. The easiest way is probably to show that they are linearly independent. Yeah, so for example, suppose they're dependent. So, okay, let's take some combination. Lambda mu take some real numbers. Take combination of this vector, linear combination of these vectors, and assume it's 0. Then what happens if I take a dot product of this with u? You get lambda u squared plus 0. Yeah, sorry, this is this is supposed to be, yeah, plus 0 because u dot v is 0 by assumption equal to 0. Since vector u is not 0, its length is not 0, so we deduce that lambda is 0. Absolutely in the same way, you take a dot product with v, and you get 0 plus mu v dot v, which is nothing but length of v squared. Yeah, and this has to be 0. Since v is assumed to be non-zero, this implies mu is 0. Okay, so these two vectors linear independent, so they span two-dimensional subspace of R2, which must be R2. Yeah. So conclusion. span of R2, span of U and V is two-dimensional. Yeah, because U and V are linearly independent, so it means this form a basis of the span. So conclusion, span of U and V is R2. Okay, because if you have linear subspace of R2, if it's not equal to R2, its dimension must be less than 2. Okay, good. Let's go to problem A2, part A. This is also true false statement. Yeah. So you have vectors U, V, W in Rn. And the question is it true that if the linear combination is zero, if they are linearly dependent, is it true that T of U, T of V, T of W is linearly dependent as well, and where T is some linear operator from Rn to Rn. T is a linear operator, and the assertion A says that is it true that if U, V, W are linearly dependent, is it true that these vectors are linearly dependent? Yeah, this is true. Why? By definition, more or less. Linearly dependent. Indeed. Why this is true? So what does it mean by definition linearly dependent? Okay. This is basically mean that we can find three real numbers, lambda, mu, delta, such that not all of them zero, such that the linear combination of U, V, and W is zero. Is zero vector. So now if we know this, we can apply linear transformation to the left-hand side and to the right-hand side of the equality. But of course, linear transformation applied to zero vectors is zero vector, because one of the properties of linear transformation, and also by the linearity, we know that this is lambda T of U plus mu T of V plus delta T of W. Okay, so this types in. And of course, this means that they are linearly dependent. We don't need this bracket here. Okay, so this is zero. So this means it's exactly vectors linearly dependent. Okay, part B of the same question, A2, is similar statement. Again, you have vector U, V, W in R2, in Rn, and the question is that, is it true if you have some linear, for every linear transformation, we have some linear transformation, and the question is it true that if these three vectors are linear independent, then the images and applied, when we apply T to them, you get three linear independent vectors. So basically U, V, W are linearly independent. Is it true that this implies that T of U, T of V, T of W are linearly independent? No, this is not true. Why? With simplest examples, take R3. basically we construct counter example. And take u to be 1, 0, 0, v 0, 1, 0, w 0, 0, 1. That's a linear independent vector. And let's take linear operator from R3 to R3. Very nice linear operator. Such that t of v is, okay, I use v here. Okay, let me put, here x, y, z. Is just vector 0, 0, 0 for every x, y, z. This is a nice linear operator. It maps all vectors to 0. Yeah. So then, in this example, t of u is 0, t of v is 0, t of w is 0. But if you have three vectors, one of them is 0, they are linearly dependent. So these vectors are linearly dependent. So this assertion is not true. Okay, let's go to the next question. Okay, the next question is problem A3. Yeah, you have two vectors, 1, 2, 3. Let's call it V1. And you have a second vector, 4, 5, 6. Let's call it V2. And the question is, the smallest linear subspace containing these vectors is something whose equation is ax plus by plus cz equals 0, where a, b, and c are something. So we need to find this something. So this something, the smallest linear subspace of R3 containing this vector, is a plane, of course, given by this equation, and we need to find a, b, and c. Why I know this is a plane? Because vectors v1 and v2, it's easy to see that they're linearly independent. We will gonna show it in a second. So the smallest subspace which contains these two vectors is a plane that passes through the origin. We need to find ABC. One simplest way to find ABC is just to take cross product of these two vectors. Yeah. Okay, this is not hard, and you just can check that this is minus 36 minus 3. Okay, so why ABC can be taken as a cross product? Because cross product is orthogonal to vectors 1, 2, 3, 4, 5, 6. And if you think about this equation, you can think of this as a dot product of ABC and vector x, y, z. So every vector contained in this plane, yeah, must be orthogonal to vectors v1 and v2. So this should be ABC, or this should be cross product of these three vectors, maybe up to scaling. Yeah. Okay, anyway, we can do this. We found this equation. We can divide, of course, this vector by 3, and we get equation by minus 3, equation of the plane x minus 2y plus z equal to 0. Yeah. So basically, everything I said till now can be considered as basically your work. It's not part of the proof. It's just preparation, warm up for the proof. Now, basically, you can prove this assertion. So we want to say that A is 1, B is minus 2, C is 1. So now how to prove this? The proof is, first of all, first of all, since cross product is not zero, these two vectors v1 and v2 are linearly independent. Because again, if we have two vectors, if they're linearly independent, that means one of them is a scalar multiple of another. By the basic properties of cross product, in this case, the cross product would be zero. But it is not zero, so they not linearly dependent, so they linearly independent. Okay, so the smallest linear subspace of R3 that contain them is the span. The smallest linear subspace containing vector v1 and v2 is the span. Since we already know that they're linear independent, the dimension of the span is 2. Yeah, but dimension of this plane is also 2. Yeah. Why? Because, for example, by the rank nullity theorem, yeah, because it's a kernel of the matrix 1 minus 2, 1. Kernel of this matrix is exactly this plane. Yes. Okay. Or alternatively, you can say that this is orthogonal complement to this span of this vector. And by the orthogonal complement theorem, this dimension of this is 2. Or another way how you can show the dimension of this is 2, observe that this plane contains this span. And clearly this plane is not R3, yeah? It is not equal to R3. For example, vector 1, 1, 1 is not contained in the plane. Okay, so actually vector 1, 1, 1, yeah, so I think it's vector 1, 1, 1 is contained in the plane. Let's say vector 1, 0, 0 is not contained in the plane. So from this we deduce that dimension of this plane should be strictly less than dimension of R3. Dimension of R3 is 3. So this should be strictly less than 3. The dimension of this we know is 2, so but the span is clearly contains here. Vector v1 is contained in this plane, vector v2 is contained in this plane. You can just check, so substitute these two vectors in this equation and you get 0 equal to 0. So v1 is contained in this plane, v2 is contained in this plane. So the span is contained in this plane. So dimension of this plane should be bigger or equal than 2 and less than 3. So it is 2. So this means that these two guys coincide. Yeah. Okay, good. Let's go to, so we solved this problem. Let's go to the next one. The next one is the problem B1. Okay, so we have vectors u, 1, minus 1, 1, and v, 3, 5, 2. And the question, are they linearly dependent or independent? Yeah, okay. First we can check this. So, okay, this is part A. Linearly dependent or linearly independent? Again, the only thing to know, or not only thing to know, there's several ways of checking this, but let's just do this by the book. We need to find when this linear combination is 0. If all such linear combinations are non-zero except for lambda equal to 0 and mu equal to 0, then these two vectors linear independent. So this gives us equations: lambda plus 3 mu is 0, minus lambda plus 5 mu is 0, lambda plus 2 mu is 0. Yeah. So for example, subtracting this equation from this equation, we get mu is 0, and substitute mu here, you get lambda is 0. So this means that they're linearly independent. Okay. Of course, alternatively, as in the previous problem, we can just take a cross product u and v. Yeah. And okay, let me remind you how to find this cross product. You can write down this vector as rows of a matrix, and here you put vectors e1, e2, e3, and take a determinant. Again, this is just a formal sum. It's basically it's not exactly a matrix. It's a matrix size that here is e1, e2, e3 vectors. So this is just a shortcut how to memorize formula for the cross product. At least I memorize this formula in this way. Yeah. Again, this is e1 times what? This minus 1 times 2 minus 2 minus 5, so we get minus 7. And then you get minus e2 times 1, 2, minus 3 times 1, so minus 1 plus e3 times determinant of this matrix 5 minus minus 3, 8. Yeah. So this is vector minus 7, 1, 8. Yeah. It is not 0, so this also implies that the vectors u and v are linearly independent. Okay, part A is solved. Let's do part B. The question is it true that 5, 4, 3 is a linear combination of u and v? Again, we can make it by the book. We can say, suppose this is a linear combination of u and v. 1 minus 1, 1 plus mu times vector 3, 5, 2. Yeah. If we can find such real numbers, lambda and mu, we're done. If we show that they don't exist, we're also done. Okay, this gives us a bunch of equations. We get 5 equal lambda plus 3 mu, 4 equal minus lambda plus 5 mu, and 3 equal lambda plus 2 mu. Yeah, like very similar to what we did before, subtracting this third equation from the first one, we get 2 equal mu. Okay, mu is 2. You substitute it's here, and you get 3 equal lambda plus 4. So lambda is minus 1. On the other hand, if you substitute it here, yeah, what do you get? You get 4, both this and this. You get 4 equal minus minus 1, 1 plus 5 times 2. Contradiction. 4 is not 11. Contradiction. So such vectors do not exist. So vectors such numbers lambda and mu do not exist. Yeah. So the answer is vector 5, 4, 3 is not a linear combination of vectors u and v. This solves part B, but we can actually solve it a little bit differently. Let me use a different color. Remind you that we found this vector minus 7, 1, 8. Minus 7, 1, 8. This was a cross product of u and v. So if 5, 4, 3 is a linear combination of u and v, yeah, it means it should be orthogonal to the cross product. Yeah, because cross product of u and v are orthogonal both to u and v, so it should be orthogonal to any linear combination. So then we can just take this dot product, and if this dot product is 0, it means 5, 4, 3 is contained in the plane spanned by our vectors u and v. Let's just check. This is minus 35 plus 4 plus 24. Clearly it's not 0. So this also implies that 5, 4, 3 is not a linear combination of vectors u and v. Okay, let's go to part C. Part C question is, can we find vector w such that u, v, w form a basis? Can we find such vector? Answer is yes. Of course, we already know that this vector is orthogonal to u and v. Yes, we can take this vector. So if we wish, for example, we can take u, v, and u cross v, which we just found. Yeah, this is going to be a basis. Alternatively, if you just forget formulas, everything, orthogonality, basically you can just think that we want to complete our two linearly independent vectors u and v to a basis of R3. There's a lot of ways of doing this. So basically, if you just grab randomly some vector, you're probably going to get a basis. The only thing you have to check that your three vectors are linearly independent, because if they're linearly independent, they form a basis in this case, yeah, because they span a three-dimensional subspace of R3, which must coincide with R3 because dimension of R3 is 3. The dimension of R3 is 3. Okay, let me remind you that vector v was 1 minus 1, 1. Okay, sorry, vector u. Vector v was 3, 5, 2. So again, I just can take the simplest possible vector. How about 1, 0, 0? Okay, so to show that, the only thing I have to show that these three vectors are linearly independent. Why they're linearly independent? For example, there's many ways of doing this, but one way of doing this, you can just check determinant of this matrix. If determinant of this matrix is not 0, that the columns of this matrix are linearly independent. Okay, let us compute. But this is just 1 times determinant of this matrix. Yeah, so it's 1 times minus 2 minus 5, which is minus 7, not 0. We're done. So this is a basis. This is also a basis. There's a lot of different bases. So part C is done. Let's do part D. Does there exist a vector W such that U, V, W is an orthogonal basis? Orthogonal basis, it's a basis consisting of orthogonal vectors. It's like orthonormal, but maybe slightly weaker. Orthonormal basis is orthogonal, but in addition, for orthonormality, we assume that length of every vector in the basis is 1. Okay, and now we observe that vector u and vector v are indeed orthogonal. Yeah, 1 minus 1, 1, 3, 5, 2. We take a cross product. 3 minus 5 plus 2 is 0. Yeah, but we already found vector orthogonal to u and v. This was vectors u cross v. We found it here. So it's vector minus 7, 1, 8. Yeah, so your orthogonal basis is uv u cross v, where u cross v is given by. Yeah, because, and you can check if you wish, if you don't trust me, if you call this w, you can check that u dot w is 0, v dot w is 0, and u dot v is also 0. So this is orthogonal basis. Any two vectors in this basis is orthogonal. Okay, let's go to the next problem. It's a little bit computational. This is a problem B2. Okay, we have this matrix A, 1, 2, 3, minus 1, 3, 2, 1, 0, 1. And part A asks us to find eigenvalues. Again, when you see the 3 by 3 matrix, the first thing you have to do is to compute its characteristic polynomial, which is determinant in this case of a matrix 1 minus lambda 2 3 minus 1 3 minus lambda 2 1 0 1. Yeah. And we just compute it by the book. Again, this is this times this plus 1 times determinant of this matrix here. So let me write it down accurately. So this is 1 times determinant of this matrix, 4 minus 3 times 3 minus lambda. Oh, to be precise, I should put like plus minus 0 times determinant of matrix obtained from this matrix by removing this column and this row, but it's 0 anyway. And then plus 1 times determinant of this matrix. 1 minus lambda, 3 minus lambda, minus 1 times 2, it means plus 2. Okay, we have to simplify. This is a long process, at least for me, but I simplified it and I get minus lambda times lambda squared plus 5 lambda plus 6. So we were lucky that actually determinant of A is 0. So this is basically means characteristic polynomial has no constant term. Yes, so it's divisible by lambda. And then everything is reduced to finding roots of polynomial equation of degree 2, which we can find using the formula, quadratic formula, or we can just see that this is polynomial factorized like this. Yeah? So lambda 1, first eigenvalue is 0, second eigenvalue is 2, third eigenvalue is 3. So remember, eigenvalues are real roots of characteristic polynomial. Yeah, so we're done. Okay. Now, part B. Part B asks us to find eigenvectors for each eigenvalue. For each eigenvalue, find n eigenvector. Okay, let's start with lambda equal to 0. Lambda 1 equal to 0, yeah. So what does it mean find eigenvector? We need to find a vector such that we have this, yeah. And v is not 0. Here, we just need to solve system of equation 1 0 1 times x y z. X y z is my vector. This gives us system of 3 equations, but actually we know for sure that one of these equations is redundant because the rank of this matrix is less than 3. So, but let me write down both of them. So now I can erase one of these equations. Which one? Basically, I know that these equations correspond to the rows of my matrix. So if I take two linear independent rows, then these rows span the row space. It basically means they give me the same system of equations. So for example, I like this row and this row because it has zeros. So it means I don't need this equation. So I just erase it. Yeah. And how to solve it? Again, I don't need to find all eigenvectors. I need to find just one. So for example, how about I put z to be 1? Yeah, then if z is 1, then x from this equation is -1. And then I have the third equation, -1 plus 2y plus 3 is 0. Yeah. So what does it mean? It means y is -1. So I got the vector -1, -1, and 1. Yeah. Okay. This is my V1, first eigenvector. Okay. Good. Absolutely in the same way. Absolutely in the same way. Let me use a different color. If I take lambda 2, let me remind you that lambda 2 was 2, then I can find its eigenvector which corresponds to this eigenvalue. And again, what it is? This is basically, I need to solve the system A minus lambda identity times x, y, z equal to 0. Yeah. Basically, I need to find the kernel of this matrix here. So when you substitute 2 here, you get a matrix -1, 2, 3, -1, 1, 2, 1, 0, -1. Yeah, you solve the system and you get the second vector. Again, there's a lot of infinitely many options for the second vector, because if you have one eigenvector with eigenvalue 2, you can multiply it by any non-zero number, you get eigenvector. So we are asked to find n eigenvector, so we can just take the one that looks simple. Yeah. Yeah, and finally, somewhere here, let me find third eigenvector. Have lambda 3. Let me remind you, lambda 3 was 3. Third eigenvalue was 3. Yeah, and I need to solve this system. I need to subtract from this matrix, from its diagonal elements. I need to subtract 3. I get a matrix -2, 2, 3, -1, 0, 2, and 1, 0, -2. Yeah, you see these two rows are linearly dependent, and I need to find the kernel of this matrix. Yeah. Okay, there are many solutions. I need just one. I need just one solution. And okay, I don't have much space here. So let me put here one solution is 4, 1, 2. Okay, good. So we found 3 eigenvectors that with eigenvalues 0, 2, 3 respectively. Okay, good. This solves problem B, part B of this problem. Part C asks us to find the rank and nullity of my matrix. Okay, we already computed determinant of this matrix and we know it's 0. So this implies rank less than 3. So what does it mean less than 3? Less than 3 means at most 2. This is not a zero matrix, so rank is at most at least 1 by rank nullity. No, not by rank nullity, just by rank 0 means dimension of the column space is 0. It means every column is 0, which is not the case. Yeah. Now I claim that the rank is 2. Why? It's enough to find two linearly independent rows or columns. For example, I can take these two columns and I claim that they're linear independent. Yeah. Proof. Yeah, these guys are linearly independent. Indeed, if they're linearly dependent, then the vector minus 1, 3, the columns of the matrix of this matrix is going to be linearly dependent. Yeah? So if rank of this matrix is 1, the linearly dependent means rank of this small matrix is 1. If this is the case, it means if I just remove, for example, the top row, the remaining 2 by 2 matrix also going to have rank 1. Yeah. So it means that this rank would be 1. But this is the same as determinant is 0. But we can compute determinant is minus 3, it's not 0. It means that these two columns are linearly independent. It means that, of course, this is also linearly independent. So rank is 2. By rank nullity theorem, nullity is 1. Yeah, nullity is in this case 3 minus rank. And what does it mean? It means that the kernel of this matrix is one dimensional by definition. But basically, we already know it. This is the kernel of this matrix. We were finding the kernel of this matrix. We found one element in the kernel, but basically our solution implies that if instead of z you put lambda, then everything's going to be scaled by lambda. Yeah, if I put instead of 1 here lambda, then x going to be minus lambda and y going to be minus lambda. So we already implicitly proved that the rank, the nullity is 1. Since the nullity is 1, then the rank is 2. Okay. And finally, part B2, part D. The question is A diagonalizable? Answer is yes, of course. Why? Because all eigen values are different. Different. Distinct. If you have 3 by 3 matrix, you have 3 eigenvalues, these 3 numbers, if all of them real, and if all of them, none of them coincide, so they have 3 distinct real numbers. Then by the results in the lecture notes and by the results we described in the lectures, this implies that matrix is diagonalizable. Okay. And then we ask to find a matrix P invertible such that P inverse AP is diagonal. Yeah, but we know if it's diagonal, it should be diagonal matrix with diagonal entries. There's going to be eigenvalues, so it's going to be lambda 2, 3 in this case, and P is a matrix consisting of our eigenvectors v1, v2, v3. Yeah, this is eigenvectors of the matrix A we found on the previous slides. Yeah, with the eigenvalue. So v1 is the eigenvector of this matrix with eigenvalue 0. v2 is eigenvector of this matrix with eigenvalue 2, and v3 is eigenvector of this matrix with eigenvalue 3. Yeah. Okay, we already found them, so I will not write them down here. Okay, this is it for problem B2, and I think this is all linear algebra problems in this exam. This is end. Okay, good. Let me stop the recording. You see, it was actually not so bad.